So start a little bit with a company overview. We're a engineering consultancy, been Australian, employee owned, and we've been operating since the late 50s. Our core disciplines are structural, civil, traffic, and facade and construction engineering. And we're predominantly focused on sectors such as education, health, high rises, and you see there the Atlassian project at Central Station, transport and infrastructure, data centers, and we also do design competitions. The one there in the image is the NGV Museum in Melbourne. We have around 350 staff. We're very present in Australia, so Sydney is our main office, but we also have a large Melbourne office, and then offices in Brisbane and Canberra. And then outside of Australia, we have Singapore and Jakarta. Jakarta has been running for over 20 years. It's a very well-established office there, and Singapore just opened this year. Cool. So the company at the core, we have the main disciplines that we show there in the orange boxes. So, and then we have a lot of other specialist services that basically support these core disciplines. Both Tim and I are part of those specialist teams. Tim is part of the timber engineering team. I'm part of the digital team, but we also have our sustainability team, the heritage, and the applied sciences teams. Cool. All right. So starting with the topic of the day. So Westgate Tunnel. The project is part timber engineering, part digital computational design. And what we're going to show here was work conducted between 2018 and 2019. So it's been over, between 4 and 5 years old, some of the stuff that we're going to show today. We were engaged by the managing contractor, so the consortium between CPB and John Holland, and our scope was to advance the architectural concept design for the timber structures, and the work that we conducted was used to award the subcontract package of this project. All right, let me turn on the laser pointer. The Westgate Tunnel is a very large project, contains other things apart from the tunnel. It serves this here on the right of the image is the Melbourne CBD, so we're west of the Melbourne CBD, and the project will deliver an alternative to the Westgate Bridge, which is shown here. It has 3 main structures: an elevated roadway section here in orange, the tunnel structure, which is shown in the green dashed line, and then an updated section of the Westgate Freeway in purple. And you probably can't see, but at the entrances and exits, which are marked with a black line there, are these portals. And we're going to be talking about these portals that are present at the entrances and exits of the tunnel. So they were designed by Woodmarsh architects. The portals feature the architectural timber transition at the leading into the tunnel and out of the tunnel. And in 2 of the portals, the 2 that we see there, these are the largest ones, the northern portal and the southern outbound portal. They also have a concrete ventilation structure with a feature aluminum clad diagrams on the back. They are large structures. The northern portal is the largest of all of them, and we show here it has around 40 meters wide, 40 meters high, and over 100 meters long.
All right. So the structural design of these portal structures requires the consideration of several parameters. So we've got materiality, durability, fulfillment, transport, and the geometry. All these factors feed into each other, and they really influence the design solutions. So we've got a timber grid shell, which is comprised of glulam diagrid members. Now, we've got smaller, more flexible elements enabling more shapes to be fabricated, which provides both structural and architectural flexibility. So originally in the start of the project, we were looking at getting glulam from Australia, New Zealand, North America as well. The preservative treatments, for a little bit of investigation, seem to be a little bit restrictive from Europe. So we ended up going down the GL10 and GL13 path. We wanted to really try and open up the market for as much timber supply as possible. We don't really want to be going down a one supplier road or specifying a really high glulam strength that would be really restrictive of the amount of suppliers that we could potentially source the glulam from. So going for the GL10 and GL13 seemed to solve this problem. So using timber externally and durability is probably one of the first components that needs to be solved. So using timber externally is very common and has been successfully adopted in many instances internationally, both on the small scale and the large scale. So the key of a durable solution here is considering the material, the preservative treatment, and the detailing. So the environment that we've got in the Westgate Tunnel, it's going to have significant humidity, it's going to have heat, it's going to have precipitation as well. So we need to really consider these things when thinking about the durability. So the detailing and the material needs to balance out a few of these considerations. In addition, the timber is going to be susceptible to birds and insects and termites. We want to be careful here. And also because it's a portal structure with cars and trucks going past, there's going to be a fair amount of pollutants in the air as well. So all these things we need to consider. Now, the BCA has some pretty good guidance on the requirements on the durability and the design life. So got this the table in green straight from the BCA. So there's some information in there. So in terms of the structural detailing and thinking about durability, we want to prevent the structure from remaining wet. It's okay for it to get wet because obviously it's outside, but what we really want to avoid is any increase in that moisture content. So able to get wet, that's fine, but we want to avoid it from staying wet. And so we want to be projecting that end grain of the timber members, developing capping details or inclined surfaces so for to fall away. This by avoiding the water sitting in these nooks, we can increase the lifespan between maintenance. So that's going to be pretty critical because the maintenance strategy on something like this is going to be fairly limited. The selection of the material for the joining system is pretty critical because there's going to be plenty of areas that just aren't going to be accessible for long-term maintenance. So in terms of the procurement, as I mentioned before, we really want to open this up to as many timber suppliers as we can. We don't want to be going down one path and just forcing the project to source from one supplier. We want to have everyone being able to tender on this project. Opens up the supply as well. So this will also help a competitive tender. So a couple of things we need to think about when we're looking at this structure like this. So we're trying to specify element performance rather than a specifically manufactured product. So we're thinking about elements, making sure element sizes are available from a number of suppliers. We want to make sure the geometry is simplified and maximize the possible supplies, as I mentioned. Timber species, treatments, we want to have this clearly outlined of what we want to use. We also want to make sure we have a little bit of flexibility around the connection type and the connection stiffness. We don't want one little connection to change and then have to go through and change everything else. So we want just a bit of flexibility in there. The standard container size for timber elements is a key consideration across any timber project, not just this project. We want to make sure we've got fits in standard containers. I'll talk about this just in one moment. But and then another point, we want to make sure we've got an agreement on the minimum maintenance period. We don't want one timber supplier assuming one thing, another timber supplier assuming another thing, and these not meeting in the middle. We want everyone to be on the same playing field. So in terms of transport, as I mentioned, so big consideration, any timber project, we try to limit the size of any timber element to fit in the standard 40-foot or 12-meter container. So yeah, sure, we can bring in larger chunks of timber, but this is going to probably result in open top containers. It's more expensive. You're going to open yourself up to damage during transport. So we really try to have it all these on standard containers. There's plenty of timber comes from overseas, so shipping container is the key requirement. And we also want to balance the transportation and the craneage cost. We don't want too many timber members and have the crane going non-stop, but we also don't want on the opposite end to lift only one element but not physically be able to get it to the site. So there's a delicate balancing act that needs to be played here. So geometry this is a key consideration on structural performance. So optimization here, this can lead to efficiency in both the strength and the performance of the structure. Now, historically, we would have done this through manual methods, physical models, but now with all the technology available now, we can accurately predict this computationally. The fabrication and element breakup is a critical consideration. So there's the appearance, both from the architectural consideration, there's the structural performance criteria, there's the balancing of number of nodes, the connection complexity, how all the nodes connect in as well. So these are all considerations we're trying to think of. And we've had two schemes in this project. We had we call the diagonal timber grid scheme, and the triangular parallel arch scheme, which we'll talk about just a bit. So this project had a number of opportunities for optimization of the form, the buildability, and the efficiency while maintaining the architectural intent. We don't want to go and optimize this thing and the architect come back and say, "Oh, it's too optimized. It doesn't match what we're trying to achieve." So originally, the timber bridge shell had a combination of straight members, singly curved members, and doubly curved members. The timber suppliers, all timber suppliers can obviously supply straight timbers. A lot of them can supply a single curved member, but not many of them can supply double curvature members. So the first thing we want to try and do is eliminate those double curved members, which I'll circle back to it in a little bit. And just to note, oversimplification, if we take this too far, can actually lead to worse structural performance. So we want to be careful here, not to go way too far. So the typology, so referring to the placement of discrete timber beams on the surface to create this grid shell. So once again, balancing the architectural form, the structural performance, and the buildability. So we were able to make slight adjustments in the shape and the patterns across the roof. And we're aiming here to really adjust the surface for the node connections. We're trying to make the nodes more repetitive and simpler. And it will be a major factor into buildability and driving the connection cost and the cost overall down.
Cool. And so we'll talk about the first scheme first. So the diagonal grid shell scheme, as Tim was saying, we tried to remove the existence of doubly curved members, and what we did was we gradually rotated these members from the base to the top to obtain the same effect. Now, when you have singly curved members or planar members, if you don't have the twist, if you remove that twist, it's going to introduce some complexities at the nodes. And we did a fair amount of optimization studies in this scheme. on the timber curvature, on many other considerations. But the one that was most interesting was the exercise that we did for the nodes, the reduction of number of nodes, which is what I'm going to talk about. So we basically, each node is shown on the nodes is shown on the left. It was a steel node, and each node family or each node type was defined by 3 parameters. So the alpha angle that we see there, so that's the opening angle between adjacent timber members. The beta angle, which is the angle between the axis of the steel nodes and the direction of the timber member when it meets the nodes. And then the gamma angle is basically the twist angle in which the timber member meets the node. Now the beta angle, so the axis between the angle between the axis of the node and the orientation of the timber member, that can be accommodated by the cuts at the end of the timber member. So the alpha and the gamma angles were deemed as the 2 true parameters for these steel connections. So in order to increase the repetition, the repeatability of the connections, we performed 2 stages of optimization. So this first scheme here, diagram here, shows the first stage. And the aim of this first stage was to simplify the geometry envelope, and create an initial timber member topology, right? So our principle here was that if we use simpler surfaces, so like cones and cylinders, you'll obtain nodes with similar properties. However, when the bounding conditions of this geometry were quite challenging. The intersection of cones and cylinders with the plane, you can get anything between a parabola, ellipse, and hyperbola, and therefore, our structure had to land on linear supports that were adjacent to the roads. So we had to have a bit of a creative approach on how we would find these simplified shapes. So what we did initially was we fit the top of the surface to a cylindrical surface patch, and that was because the geometry itself already was very close to it. And then the problems that we were trying to solve is, okay, what is the conical length? So what is the cone that is tangent to the cylinder on the top? So tangent that has the same position, and then that would land exactly where we needed to at the base. So we used some genetic optimizers here and some gradient descent optimizers to find the parameters of those cones, and we did that for the rest of the geometry envelope. So here are some strips of those rational shapes that we identified, and when you trim it and stitch it together, you get something like this, right? So the result consisted in 7 surface patches. So three of those were cylindrical surface patches, 2 were conical, and 2 were freeform, the green at the back. And the freeform was, we resorted to freeform at the back because due to its complexity, and again, it would have an impact on angle repetition, as you will see later, but we thought this was a pretty good start. Then the next step was to find the cells, right? The topology of the timber grid shell. So the idea to start with, we started at the cylinder again at the top, and in order to find these rhomboids, these diamond-shaped cells, what we did was we used geodesics. Okay, so geodesics here, we're defining them as the shortest distance in curved space. We usually define them by a start and end point, right? So if we look at the geodesics on a cylinder, a geodesic on a cylinder is a helix, and by basically generating a helix and then basically translating it and mirroring it, so basically making a copy of it and generating these patterns, you get really interesting properties, because all of the nodes that you obtain at the top on the yellow area, those nodes are going to have all the same properties. They're going to have the same alpha angle, the same gamma angle. So we thought that was really interesting. On conical surfaces, you don't get the same properties. So the red patch here, that we see. And but however, they allowed us to have already little variability. So what we started, in order to generate those geodesics, what we were doing was we're trying to find a set of curves that satisfy two criteria. So we try to be tangent to the top member, and they would have to be as parallel as possible to each other. So the curves that we would generate in this patch here. So basically what we're doing is we're finding an optimization problem, which was we knew the start point of the geodesic at the top because it had to meet the members of the yellow cylinder, and we were basically finding what is the position of the geodesic at the bottom, and we were varying its position along that green line that you see on the bottom. And running this optimization problem, you obtain a topology, a starting topology that you can start to work with. That topology already still had some variance, so we had to further improve it. This diagram here shows what was the second stage. So the second stage aimed to grab the previous topology and further optimize it. And we did that in 3 stages. We started by first clustering, so clustering the alpha angles, so trying to reduce the variability in alpha angles. We did the same for the gamma angles, and then at the end we just calculated what are the final node and member families. So for the alpha angles, we used a technique called dynamic mesh relaxation. So for this purpose, we use Kangaroo, which is an add-in in Grasshopper, and we use it as a form finding approach. We modeled each mesh edge, so the timber members, as springs, and we applied forces to these members in order to change their configuration. So the forces that we applied were the forces to the alpha angles. So we were basically grabbing every pair of adjacent timber members, and we were applying a force trying to push the mesh into having the angles as we needed them to. So what we did was we calculated the angles, the alpha angles across the whole structure. We identified target alpha angles that we wanted each cell to have, and then we applied the forces to push them into those target angles. What you see here is actually the error, so the difference between the target angle and the actual angle. And you see that at the back, we get these blue and red colors showing that error is actually quite high in there. So we wanted to reduce this error to a minimum as possible. And this is a video displaying how the mesh relaxation would progress. So as the nodes change shape, the error would be reduced until we reach a configuration. And this image here shows the before and after. And you can see that, you know, these error tolerances are quite small after the mesh relaxation. So from a histogram perspective, so on a more statistical perspective, what we see here is on the x-axis is the alpha angle for each pair of timber members, and on the top you see the number of pairs with a certain alpha angle. Before the relaxation is shown in blue, and you see how wide the angle is before we produce the mesh relaxation. And then in orange you see after the relaxation. So you see that the range of angles is is much more narrow, and therefore we were able to bring those angles to a smaller variability. So, and then the alpha angles was a bit, the gamma angles, apologies, were a bit simpler. We just based it on what was the surface curvature at a specific location and in aesthetics. So we worked with the architect to vary these twisting angles across the geometry in order to, you know, simplify and have a very a look that would be very close to the architectural intent. This is just an image showing those angles. The cylinder has very well set angles, and then the cones we also prescribe some target angles. Cool. So at the end, we calculated the cluster families. You see that we were able to. There was one cluster family, so marked as 0, shown in red on the sides. That node was repeated 175 times, in total, we reduced by tenfold the number of node types, which we thought was a pretty good outcome. But for the triangular grid shell.
So a second scheme was explored. So we had the diagonal grid scheme for scheme 1, and scheme 2 ran with a series of parallel hoops rather than a diagrid. So this is a long section through, and as we can see in red, we've got the series of parallel timber arches, timber hoops. So this is the second scheme which we look to explore. So the goal here is to improve the efficiency of the nodes. As I mentioned before, we're thinking fabrication, installation, and cost. So there are 3 big factors that it's going to influence the structure. So we're once again trying to reduce the overall cost. So I've got a table here showing the relative cost of glulam. So straight glulam that glulam producers have, that's a cost of 1. And so as soon as we start to introduce singly curved glulam, that cost jumps up to about 2 or 2.5. But as soon as you introduce double curved glulam, the cost jumps up between 6 to 8. So that's a pretty hefty jump. So the step 1 is to try and produce all those doubly curved glulam members. So in our parallel hoop system, we've got a single curved glulam arch, and then connecting between the arches are a series of straight glulam. So we've already been able to reduce the cost down by eliminating these double curved glulam members.
Yeah. So in terms of the rationalization, we had to have this sort of consistent approach across the whole thing. So we just use the pace of the parallel hoops in the timber section, and we just we use that as generating planes for the aluminium. However, that's not the topic of today's talk. I think the work that was more interesting was the detailing the connections, as we'll see.
So triangulated structure helped to reduce the demands on the connection. We're trying to reduce the complexity. So there's a couple of different types of connections on this project. So obviously, because we can't deliver the glulam curve members in one member, it'd be too large to transport. We're going to have to connect this on site. So we're going to have timber to timber, we're called the hoop to hoop connections. So they're going to need to have some significant splices in them when it gets delivered on site. And so what's going to happen, we're going to have a large number of steel dowels connecting the timber glulam member to the steel connection. All these dowels are going to be shot fit because we will want a high degree of accuracy. And so they'll come to site, and we'll aim to have the steel to steel, so where these members are coming together, all bolted. So bolts, there's going to be a lot less bolts than there are going to be dowels. So being able to connect this on site is going to be easier than trying to dowel the timber as well. So we're going to be able to split those two fabrication and installation requirements out. And then we're going to have, in addition to our hoop-to-hoop connections, we're going to have the actual diagonal to hoop. So where the straight glulam comes in and connects to our primary hoop. And this was done with a series of steel plates. So I've got an example connector here of the timber diagonal to the hoop. And so we're trying to come up with ways to make this easier to fabricate and easier to install. So there are things like scribing the member identifiers on. So in this image, we know we've got member C35 and we've got J2 and J8, for instance, connecting in. So we want to make this easy to identify on site and knowing what connects where. Furthermore, we want to have a series of call them jigs or templates. So having a series of these made up and temporarily next to the cleat plate and welded to give a high degree of confidence and accuracy on these angles that do come in, because those angles are quite important.
Yeah. So in regarding these jigs, one thing that we found quite interesting in this study was that it's quite simple and minute, but still interesting, was how can we reduce the number of types of jigs that we have in this project. One approach that we did was, here we see basically a main hoop member, so the principal hoop members, and this one here is one of the secondary die-grids members. And what we did was we wanted to have this alpha angle, right? This opening angle between these two to be as similar as possible across the structure. And one little trick that we applied was just by rotating slightly. Now, this is obviously an exaggeration. It's an exaggerated rotation, but by slightly rotating the gamma angle, we were able to bias these alpha angle. So in this example, by rotating gamma, by increasing gamma, we were also increasing alpha. So we were adjusting the orientation of these secondary die-grids ever so slightly, just to obtain obtain a set number of alpha angles without affecting the aesthetics, obviously.
So the structural engineering of these is quite exciting. We had the opportunity to be able to not only analyze the structure, but then come in and optimize the actual structure and the connections, and being able to rerun the analysis and have a little bit of let's say architectural input would help really drive the efficiency of the structure and the cost. So something which is great for TTW to do was have this input.
Yeah, it was actually quite a, you could clearly see how it fits our specialties here. Like our team would be, dedicated to the architectural geometry component, so to the geometry optimization part, and our timber engineering team would couple it with the engineering, and we created an integrated system that allowed this sort of process to be fully integrated from the geometry all the way to the structural engineering and the costs.
So in terms of the actual structural optimization, so obviously we start with a geometry which we feed in to a 3D. That's there was a grasshopper script that was basically coordinating and basically pushing the levers. We would take that structural geometry and would perform the next stages. So from that, we're able to have our structural analysis. We're able to run that. We're able to extract the results. We can run it through our own timber analysis software. We can then run it through an optimizer, which we'll chat on in just a second, and then we can rerun once we keep running this loop until we find a converged solution, and we can eventually produce the timber design reports.
The optimizer was quite simple. Basically, what it does is it has two thresholds. The upper threshold, if the utilization ratio of a certain member would be above that upper threshold, we would deem that member to be overutilized, and therefore we would increase its size. And then the lower threshold, if there was a timber member that had the utilization ratio below that lower threshold, we would deem that member to be underutilized, and therefore we would decrease its size. In between those two thresholds, we had what we call a lazy zone. So that's a zone where nothing really happens. That's the acceptable zone for that certain member. And then we ran this for strength and for buckling too. So we did both of those. We reached this is the diagonal grid shell. So we for this particular case, we ran an optimization for each individual timber member. The architect didn't enjoy the variability in the aesthetics of having heterogeneous timber section sizes that you see here on the left. So we ran then a second optimization, which only took two sizes, one for the main arch here at the end, and then another size for all of the typical members at the back.
So there's a similar process that's gone through for the parallel hoop arch. The image on the left, once again, there's an option of having all different members, all optimized. And then there's the second option where we've only got two sizes. We've got one size for all the parallel hoop arches, shown in pink, and then we've got an option for the timber diagonal infill members. So we're able to have two options there optimized, and by placing the limits on the depths and the widths and the width range, we've been able to come up with a couple of different member sizes. And the beauty of having the setup from the previous slides, we can rerun the analysis model from the GL13 into a GL10 and easily change the strength grade of the timber to then see what the implication is on the member geometry. So having all these processes in place really sped that up and not having to start again from scratch. So to summarize, so we had our original scheme, the original diagrid, and our parallel hoop system. So each portal is comparable in timber length, but the saving on the project is through the actual volume of the timber. And by improving the geometry, we've been able to rationalize the node type complexity and connections down. So that's where, by decreasing this, that's where the majority of the cost savings has come through.
We're about to describe here the table. So in these rows, we have the different portals. The first row is the diagonal grid shell, and the second one is the triangular grid shell. And as you see, the biggest drop in weight, total weight, was actually in the timber to timber connections, but also in terms of volume, as Tim said. But yeah, clearly the second structural scheme not only simplified the detailing, but also really severely reduced the total tonnage, both for timber and for the steel to steel. The timber to timber connections.
So that sums up our involvement with the Westgate Tunnel. We do also do a few other timber structures, which I'll just touch on briefly. Obviously, everybody knows, or probably should know, the Atlassian building, which is currently under construction. That's going to be a 40-story tower of hybrid construction. So got a couple of images there. That'll be very exciting once that's completed. Recently completed is the Bond in Northwest. That's a commercial building using timber post and beams. So that was completed last year. We also do timber, so CLT floor and wall systems. AVO Northwest, which is a aged care facility in La Trobe University down in Melbourne. These are a couple of years old now, but this is some of the other projects we're doing. I've done recently completed Florida University Law School, once again earlier this year, I think it was. So that's recently completed. We've also Bungiel Place, that's old now, but that's another, as you can see, it's a pretty familiar structural form, as we've been talking about. And continuing on the schools as well, Barker College was recently completed, and we've also got a social housing project under construction at the moment. So that's in Glebe. That's a CLT floor and wall system. So that's, like I said, that's under construction now. So it's also in the works. And the hub at Glulam up in Port Macquarie, that's a timber walkway through some trees for and that's under construction as well. That should be completed by the end of the year. And also Westgate Tunnel, which we're also obviously talking about.
Yeah, and then we, us in the digital team, we operate mainly in areas that touch engineering projects, BIM, technology, and also software. We tend to tidy them up in engineering workflows, where we come and develop workflows and automated processes to deliver projects. Algorithmic design, where we touch more, more the concept design phase, things like complex geometry and structural optimization. So we touch a lot of that, and then also software development. So we develop tools internally for our colleagues, but also externally for our clients, and we also provide software consulting services. And that's pretty much it.
So yeah, that concludes that. If you want to reach out on any timber questions, reach out to me. I'm happy to always up for a chat. If you've got any digital questions, reach out to Andre. Hopefully be happy to talk through anything. Absolutely.
Thank you so much for the presentation. That was great. We got a couple questions that came throughout the presentation. So we'll walk through them. First one is, once this progresses to detailed design, how do you think you would address tolerance in the design when it comes to greater deflection in the temporary case? Will the member stresses change much, do you think?
Sorry, could you repeat that again?
So the question's asking, if I'm interpreting it correctly, how tolerances in design would affect the progressive construction of the grid shell, because you could imagine that if you had any slop at all, you might not match your triangle on the opposite side. So
definitely, yeah.
So how would you address that?
We did run staging analyses on the timber, and we had into account not only connection tolerances, but also the creep effects on timber. But yeah, that is a super hard problem to solve, and it was one of the big challenges in terms of the engineering. I don't have any specifics here. I didn't conduct that part of the study, but it was considered, and yes, it's a really good question. It is definitely something we accounted for, mostly around the analysis and around the staging analysis that we conducted.
Thank you. Next question is, being fully exposed in service class 3, is it expected and acceptable for the timber to turn and remain grey over its lifetime?
That's probably more of an architectural thing. Timber naturally is going to turn grey when it's exposed to the UV, unless you're going to continually sand it down and apply the protective coatings. It's always going to be turning grey. So from a changing color perspective, that's going to be more an architectural thing. Mm-hmm. Obviously, service class 3 gets designed, so all the structural implications are already designed in.
Well, it feeds into a different question we have here, which is about long-term durability and what the maintenance structure and service schedule actually was. Because I imagine if it was the client's desire to maintain the color, that could be implemented, but you'd be coating the structure annually, at least, I would expect.
Yeah.
What was the maintenance structure that was landed on?
Oh, I can't recall.
Which one?
The maintenance structure.
I don't recall. Yeah, as I said, this is work done for more than over 4 years ago. Yeah, good question. We can figure that out and get back to you. Yeah.
What was the other question here? This project was obviously a desktop study. Was the project expected to be completed? Is it going ahead?
Yes, it is. Yeah, they had some big issues a few years ago with some PFAS that was digged out of the soil. It came on the news even. They had these mounds of contaminated soil that they couldn't they couldn't process it, and therefore that pushed the date by a year, I think, or two. Wow. But it is under construction now, and it's I think it's due to be ready either, I think, next year from what I see, but don't quote me on that.
Soon. What type of maintenance would you expect that to be?
Obviously, you're gonna have to conduct probably yearly. I'd be having yearly inspections of it and how that actually looks. is probably going to have to be determined by the actual final timber supplier and sign off whoever designing it. But certainly you'd be having yearly inspections as a minimum. What this looks like and how involved it is up for discussion and input.
Did you consult with steel fabricators when you were designing those nodes?
I believe we did, to try and get feedback on the scribe marks and having the jigs and how we go and accurately have these steel cleats prefabricated and having those dimensional tolerances in there, getting their feedback on what's easy to build.
Because obviously a key part of the node rationalization is on top of the assumption that less variety is going to make the whole process easier for every stage of that long supply chain.
Exactly. You don't want 1,000 individual nodes and be trying to find the steel cleat plates in the pile.
No, and the margin of error would just compound incredibly.
Yeah, exactly.
I've got a question here. Were standard connectors like Simpson Strong Tie considered to reduce costs?
Probably.
Yeah. Say it again.
Standard connectors.
Yeah, we did consider a bunch of them. I think I can't remember the specifics on their capacity, but yeah, several of them were considered. We're just showing the end of two long stages, and in the process, yeah, we definitely standard connections were our first option, obviously. And when that was not possible, then we went to customized bespoke connections.
It was a cost optimization, correct?
Yes,
so
exactly.
Yeah, it's the optimized out is the answer. Which is interesting. What is the design life for this structure?
I remember. I think it was 50 years. Yeah.
Yeah, the optimization, that freeform part, like that sculpting with mathematics that you guys did, it's fascinating. How long did that process take, and how many revisions did you hit it with the architect pretty early on, or did it take a few times of them, you guys putting in long hours trying to get this mathematic sculpture to be beautiful, and then the architects disregarding or asking for tweaks and revisions? How was that process from a collaboration point of view?
Yeah, no, at the beginning, obviously, we were received with a bit of skepticism, which is understandable. And I think the first meetings, what we wanted to ensure with Marshall is that we would respect their vision and their design. And I think once they understood that, they kind of used us as a sort of like an extended set of resources, because they trusted us to deliver it. But yeah, in the beginning, we had a few meetings where we just came with some of our concepts, and then we use that as a bit of a kickstart for what came next. But most of the times, what happened was we would produce a design or a set of designs that would take us maybe about 4 days to do the whole process, and then that would include some renders, some renders that we generated for the architects. The architects would give us some comments, we'd highlight areas where they would be happy about, and they would come again and we reiterate. We did that a few times. We did that maybe for both schemes. In total, we might have done that probably 5 times, if I remember correctly. Then we also did some work on the back on the aluminum cladding. That was a continuation of the effort and the collaboration. So yeah, it didn't stop at the timber. We continued to work with them, and it was very fruitful. We certainly learned a lot from their what they were envisioning from the perspective of the architect, like what they wanted aesthetically. And I feel that they also got from us a really good service on coming up with rational approaches that kept their design very much alive and intact. So that was really interesting.
Have you used this method and this script? I mean, I imagine you've used it in some form, but yeah, have you used it, and in what form have you used it since then?
We've used it in a few other projects. So the principle itself, it's obviously not constrained to timber as a material. We've used it in timber projects, but we also use it for other steel projects and concrete projects. The principle being you have a component of structural analysis, and it means that you have to have a process to go from architecture to analysis, and that process to automate takes some work. Then the analysis gives you some forces. You feed those forces into some sort of designer. In this case, it was a timber designer, but we use many other types of design tools. And then with the outcomes of the design tool, that informs the optimizer what to do with the parameters. In this case, were member sizes. So yeah, so it was that the templates, we use it in many other projects. The code that we generated for Westgate, I think the biggest outcome and what we reused the most were the timber design libraries, because I think, again, this was done in 2018. We've evolved a lot since then. So we use different optimizers, different approaches. We're a bit tidier, we're a bit less reliant on Grasshopper. So things have evolved, but the template is what really remains, and a lot of lessons learned, obviously.
Thank you for sharing that. It's really interesting, because it's fascinating seeing the evolution from, say, bundle place, which is a lot more sculptural, but very, very similar in its form. Double curvature, massive variation in depth of beam, to the Westgate Tunnel, which is far more rationalized, but still has that same core aesthetic. And I hope more of these projects can come alive all across the world, because it certainly makes a humdrum highway a lot more interesting.
Absolutely.
Well, one final question for you, and that what is the species of the wood that ended up being selected, if you know?
I think it's kiwi wood, I believe. New Zealand.
Yep. It might not be a spruce then.
The pine or spruce. It'll be GL10 or GL13, so either a pine or a spruce.
Yeah, the contractor that took the project post tender, they had their own engineers, and they like to work with them. So we were not involved in the construction phase. So we've been away from that that sort of construction phase part. But
any of this final stuff, we would as I said, we're just not involved in it, so it's hard to comment exactly on that.
One more interesting one. Did you test the design with physical models or just rely on the software?
No, we did some in the beginning when we were trying to come up with node connections. We explored some early 3D printers, which were not as the closest we got to physical modeling was more for the detailing. I don't know how useful that was, but it was fun. But yeah, we didn't do any physical models. We relied a lot on finite element analysis to simulate the behavior of the structure.
Beautiful. All right. Well, that answers pretty much all the questions that we have. And I'd like to thank you again. Thank you so much for being here and offering your time to walk us through this very involved project that I'm sure will inspire a lot of people about what can be done with wood. So thank you very much.
Thanks for having us. WoodSolutions. Yeah. Thanks, guys.
Before I go, I will just share my screen again and take us through to the end. Cool. So, yeah, thank you again for that presentation. Really, really insightful. This is a reminder, the Timber Design Awards are on again this year. The awards night has been announced for this year. It's on the 2nd of November in Melbourne, South Bank. So if you're in Melbourne and you want to come and check out the latest and greatest in Australian timber design and what's happened in the past year, then come on down and get your tickets. The next series in this webinar is going to be a little bit different because of Melbourne Cup Day next month. So the webinar is going to be shifted 1 week to the 14th of November. It's also going to be at 5:30 p.m. That's because this webinar series is going to be about the upcoming changes to AS6 and 84, and it's going to be in conjunction with Standards Australia. So make sure you don't miss that one. Slightly different day of the month, slightly different time of the day. So make sure you note that in. And with that, thank you very much, and we'll see you at the next webinar. Thank you.